So to round out this unit, I want to introduce a very important and foundational concept to organic chemistry, and that is the concept of what we call multi-step synthesis. Simply put, this is just a way to build complex molecules from simple ones. And generally, that requires using multiple reactions. Now, when I say multiple, I just generally mean more than one. And so right now, this is going to be somewhat easy. So I highly recommend taking the time to master it now so that when we go on to other functional groups, we're basically what I'm giving you are tools like in a toolbox. And when you go to do a project to build something, you might not use every single tool in your toolbox. In fact, if you do that, it'll probably be very tedious and you use, way too much work, way too much time. It's the same thing with chemical synthesis. Just because you have all these tools doesn't mean you have to use them all, but they're there in the event should you need it. So what these kind of diagrams represent are the versatility of all the reactions that we have talked about, mostly from this chapter. Notice here, if we start with an alkyl halide, how many different pathways we can go down. Like all of these here, we're using nucleophiles. And you're like, well, this is way too much. I mean, should I memorize all those nucleophiles? I mean, it would be helpful, but if you just remember the key concept of if I take an alkyl halide and react it with a nucleophile, and you should know what a nucleophile looks like, you're just going to do a substitution. Or if you take something like a bulky base or sodium hydride, you can do elimination. We talked about starting with an alcohol and going to an alkyl halide using HBr. We talked about making tosylates, which are great for doing all these other nucleophile reactions. I'll just toss it in here. And the second diagram here just kind of shows, all right, here's what we can do with a tertiary alkyl halide. And again, just to add to this, we can take these tosylates, react them with the nucleophile to do substitution reactions. We have all these elimination reactions we can do. So these are kind of just some generic pathways for how we can use the reactions that we've learned even just from this unit. So let's kind of jump into some problems. One of the tactics that we use to design a synthesis is to actually go backwards. We call this retrosynthesis, where we start with our target. So this is what we want to make. So again, retrosynthesis just means go backwards. And we use this kind of arrow here as a retrosynthesis arrow. What you want to imagine is how I can split this up into two pieces. So one of the more logical things to do is just, well, split it up around the oxygen because we've talked about oxygen nucleophiles. So let's say I imagine breaking this up. And if most of my reactions in OChem are about nucleophiles reacting with an electrophile, I need to have something here that would make this carbon have some sort of character, positive character, and I need to have this oxygen have some sort of negative character. Actually, I'm just going to put them in parentheses, not like these aren't really formal charges. So how do I get this carbon right here to be electrophilic? Well, I'm going to put something that's got a lot of electronegativity on it. And how do I get this oxygen to be nucleophilic? Well, let's just give it a negative charge. We've seen nucleophiles where the oxygen has had a negative charge. And if I think about this, what kind of reaction will this do? Well, this will undergo an SN2. Switch colors here. Now I'm not kind of completely done. I got down like how I'm going to do this, but the other thing I need to think about here is stereochemistry. Notice what direction this whole group is going in right here. So what does that mean for the reaction I'm going to build? Well, that means, and I'm going to go down here and go forward now. I'm going to start with this alkyl halide. I'm going to react it with this nucleophile. And if I really want this to do an SN2, so I get that inversion of configuration, I'm going to ensure that by picking a polar aprotic solvent. You say, which one do I use? We would figure out what the best one is by doing experiments in the lab. But right now, since really don't have experience with all that, just pick your favorite aprotic solvent, DMSO or acetone or any others that were in that list. And that will get us to our desired product. All right, let's look at another one. So how do we design this? Well, again, we can look at kind of focus in on the oxygen. And let's imagine, well, if we could either break that bond or say that's the new bond that's formed, or this one. Sometimes it matters, sometimes it doesn't matter which way we pick. A lot of times we have to draw out both ways and see which one's better. So let's look at the blue pathway here. So if I imagine the blue bond there breaking, I'd have some sort of alkyl halide reacting with this nucleophile, because this would just do an SN2, and that would give me my product. Well, what does the red pathway look like? Well, in this case, this, oops, would be my nucleophile, and this would be the substrate. And here it doesn't matter which I pick. Both of these pathways on paper are equally viable to do the nucleophilic substitution we'd want to do. What's the best way? We'd have to go into the lab and try both of them and see if we get one, maybe one of them has a more of the major product, or maybe one's a lot faster. We would just have to figure that out. We just have to try it out in the lab. All right, well, how about something like this? Again, let's say this is our target. How are we going to make this? Well, ask yourself, how do I make an alkene? Now, this is where I said this is easy in the beginning here because we have very limited number of reactions and very few choices to make alkenes. Down the road, we'll talk about a lot more ways, more tools to put in your toolbox. But right now, the only way we really know how to make an alkene is to do a beta elimination. Well, what does that require? Well, we need some sort of substrate, so like an alkyl halide. Now, in order to do a beta elimination, like for example, let's say E2, I need a really strong base. But should I use a small base or bulky base? How do I know which one to use? Well, look at your target. Is that the most stable alkene that can be formed? Or is that the less stable alkene? That's the Zystaff product because it's the more stable alkene versus, say, this one here that I kind of marked there in blue. So I need to use a small base. So maybe this case I use sodium hydroxide and heat to push it towards making mostly um, the E or going through the E2 pathway. Now, what if I wanted to get the Hoffman? What if my target was the Hoffman elimination? Okay, well, let's outline all the possibilities here for what I could start with. I could start with, again, the same alkyl halide as before. Um, what's my other possibility? Could I start with this alkyl halide? I want you to think about that for a little bit. Let's go back to our first possibility here. How could I accomplish a Hoffman elimination? I want the less stable product. So I need to use, or I should say less substituted, which is the less stable alkene. I need to use a bulky base. So here I could use a base like tert butoxide. Um, I could use one of the other ones like DBU or DBN. Pick any of those is fine. But if we look at our other possibility here for alkyl halide, why is this not a good choice to start with? Because I could use a bulky base to get this, but it would also result in another constitutional isomer. I don't want to pick reactions that will lead to multiple constitutional isomers. The reason for that is I have to now spend a lot of time purifying it. So that's more time I have to use. That's more reagents I have to use. It's more costly. And so I want to, when I design synthesis, I want to try to pick reactions that will lead to one major product and minimize all other potential products. All right, so let's look at one more. And this one's going to involve multiple steps. All right, so we walk into a lab and you say, well, maybe you're in a chemistry, manufacturing company, and your boss comes in and says, you can use this compound. I need you to design a synthesis to make this. Now, as a side note, us chemists, we use these kind of double arrows here or multiple arrows to signify that it means we need to take multiple steps. So this is not a one-step process. If you look through your notes for all the reactions we've talked about, there is no way to go from an alkane to an alkene in one step. It can't be done. Okay, so what we're going to do is we're going to go through this process of working backwards again. Let's imagine what that alkene used to be. How do I make an alkene? What kind of substrate do I need to start with? Well, I'm going to start with an alkyl halide. because I can do like an E2 elimination really easily on a tertiary alkyl halide. Now I'm going to go back. I'm not going to draw any reagents yet, just kind of working backwards. Do I know a way to go from an alkane to an alkyl halide? Yeah, we spent a lot of time on that. We looked at free radical halogenation. We can replace this tertiary hydrogen here with a halogen by doing a free radical halogenation. So we have this pathway now. By going backwards, we did this retrosynthesis. Now all we have to do is outline the specific reactions that will accomplish this. Okay, so how do I do a free radical halogenation? Well, I need bromine and light. That's what we learned when we talked about free radical halogenations earlier. So that'll get me to the alkyl halide. And I said, well, I need to do an elimination here. What sorts of things will do that? Well, let's use a strong base and a lot of heat. And that will do mostly the E2 elimination. All right, so as I said, this you'll have some simple ones you'll need to do for synthesis for right now. But we're going to look at more tactics as we progress and as we get through more and more functional groups and talk about more and more reactions. That's why I highly recommend spend some time mastering this now, because the concepts you master now are going to be super applicable to when we highlight multi-step synthesis using a number of consecutive reactions, sometimes anywhere from 3 to 4 to 5, even more multi-steps, even more multiple steps than that.